This is another very interesting problem from the MIT 2023 Integration B finals, and this was problem number 1. Um, as you can see here, it's the integral of the cube root of tan x over sine x plus cosine x squared from 0 to pi over 2. Now, this problem looks very simple from the very outset. But it is a very, very complicated problem. It's a monstrosity of a problem. And we're going to see how we'll solve this problem. It's a very long problem. For those of you who need a cup of tea to follow the solution, please get that cup of tea before we begin. So the integral can now be simplified as follows. The cube root tan x over sine x plus cosine x squared equals to now, by expanding the denominator, cube root tan x over sine squared x plus 2 sine x cosine x plus cos squared x. Then bringing the sine squared x and cos squared x together, we know the identity of sine squared x plus cosine squared x being equal to 1. The integral now gets simplified further to cube root tan x over 1 plus 2 sine x cos x. Now, we can now substitute for tan x by saying let t equals to tan x, and therefore dt dx is equals to sec squared x, such that dt is equals to sec squared x dx. Using the identity, sec squared x equals to 1 plus tan squared x. That becomes dt over 1 plus tan squared x is equals to dx. Now substituting for tan x with t, we now have dt over 1 plus t squared equals to dx. We would also like to know what sine x and cos x is or are in terms of t. We can use a triangle, and the base angle being x, and since we know tangent of that angle would be opposite over adjacent, which would be now t over 1, the opposite would be t, and the adjacent would be 1, and therefore the hypotenuse would be 1 plus t squared square root. So since we know the sine x of that angle x is opposite over the hypotenuse, that will be t over 1 plus t squared, and we know cosine x is adjacent over the hypotenuse, which is now 1 over square root of 1 plus t squared. Now we can go further and substitute for those. In the numerator we have cube root of t, and where we have sine x, it's t over square root of 1 plus t squared, and then where we have cos x is 1 over square root of 1 plus t squared, and where we have dx is dt over 1 plus t squared. Now multiplying these together, we get denominator being 1 plus 2t over 1 plus t squared. Now we can multiply both the numerator and denominator by 1 plus t squared, and therefore the integral now becomes simplified as follows, and the 1 plus t squared values here can cancel, and so you are left with the integral of cube root of t over 1 plus t squared. Now I forgot to also highlight that the limits here also now change as x tends to 0, tan x tends to 0. As x tends to pi over 2, tan x would tend to infinity, and so the limits would change appropriately. Now, having this cube root here is a little bit painful, so we would also like to substitute for that, and would say now let u be equal to cube root of t, such that u cube is equals to t, and then 3u squared du would be now equal to dt. And so we would substitute for that, and obviously the limit would remain the same, 0 to infinity. And so the numerator would be u, denominator there where we had t, would have u cube, and the squared there remains. And then for dt would substitute 3u squared du. And so the integral now becomes 3u cube over 1 plus u cube squared. This is where now our problem begins in earnest. One, we would want now to expand this so that we would get partial fractions out of it. And so 1 plus u cube is the same as 1 plus u times 1 minus u plus 1 u plus u squared. And the square here now can be attached to that, and we can expand it out so that we have a over 1 plus u, and since we have repeated functions or polynomials here, we would also do now b over 1 plus u squared. And then since 1 minus u plus u squared is also repeated, we would begin with first in the numerator, a polynomial 1 degree less the denominator, cu plus d over 1 minus u plus u squared. And then for the repeated term, which is u plus f over 1 minus u plus u squared squared. So we can now again try to recombine the denominator, and then we multiply the appropriate polynomials to each constant as shown here. So now we would like to equate the numerators on the left hand side and the right hand side. But before that, we would like to reorganize so that we have the constant, and then we would have the u term, the u squared term, the u cube, u to the power 4, u to the power 5 term organized together. So as you can see here, by expanding first the polynomials, and then we get for a, there's 1 minus u plus u squared plus u cubed minus u to the power 4 plus u to the power 5. We expand for b as well, and for c and d and e and f respectively. Okay, so now for the constant term a plus b plus d plus f is without the u term, and then for u would have minus a minus 2b plus c plus d plus e plus f u, and then for the u squared we have a plus 3b plus c plus 2e plus f all the way to u to the power 5. Now we know the numerator on the left hand side is composed of only the u cubed term, so such that this initial term a plus b plus d plus f is equals to 0. The second term of u minus a minus 2b plus c plus d plus e plus f is equals to 0. The third term a plus 3b plus c plus 2e plus f equals to 0. And then the fourth term that corresponds to 3, a minus 2b plus d plus e equals to 3. The u to the power 4 term also is equals to 0, minus a plus b plus c plus d equals to 0. And then the u to the power 5 term plus a plus c is equals to 0. So we ideally, laying down the simultaneous equation appropriately as shown in the previous slide, um, we will take advantage of a plus c equals to 0 and say, okay, let's eliminate the c term in this other equation. So since we know a plus c is equals to 0, then we know c is equals to negative a. So in the first equation, a plus b plus d plus f is equals to 0. We don't have any c term there, so that just remains as it is. In the second equation, we have the c term here at the third position. So we just say minus a minus 2b minus a in place of c plus d plus e plus f is equals to 0. Therefore, negative 2a minus 2b plus d plus e plus f is equals to 0. And then the third term again for the third equation, we have a c there. So we have now a plus 3b minus a plus 2e plus f is equals to 0. That now results to 3b plus e, 2e plus f is equal to 0 because the two a's cancel one another. And for the fourth equation there, because we don't have the c term there, it just remains as it is. A minus 2b plus d plus e is equals to 3. And then the fourth term there, we have c at the third position, so we substitute with negative a, and that becomes minus 2a plus b plus d is equals to 0. So I feel like we could take advantage of this last term and substitute for a, such that a is equals to b plus d over 2. And so we can eliminate a. In the first equation there, a plus b plus d plus f is equals to 0. That now becomes b plus d over 2 plus b plus d plus f is equals to 0. And that results in through 3b plus 3d plus 2f is equals to 0. Second equation, we substituted already with b plus d is equals to 2 over 2. And because there was two a term there, so that cancels out of the denominator, and so we are left with now minus 3b plus e plus f is equals to 0. Fourth term, since we don't have an a term there, it just remains as it is. And the fourth equation, we have a at the beginning, so that becomes b plus d over 2 minus 2b plus d plus e is equals to 3. And that now results into minus 3b plus 3d plus 2e is equals to 6. And then the last equation there, we don't have any a term, and so we have our equations listed as shown here, all the four equations. So I guess the next temptation is to try and eliminate b. So we could now say eliminating b would mean that since minus 3b plus e plus 2f is equals to 0, b is equals to e plus 2f. So we'll begin by substituting for b in the first equation there. And so we have if 3b plus 3d plus 2f is equals to 0, then 3 times e plus 2f over 3 plus 3d plus 2f is equals to 0, and then 3d plus e plus 4f is equals to 0. And again, if 3b plus 2e plus f is equals to 0, we substitute for b there, and so 3e plus 3f is equals to 0. Lastly, since minus 3b plus 3d plus 2e is equals to 6, we substitute for b there, and we get 3d plus e minus 2f is equals to 6. Again, the temptation would be to use the second equation here, such that we would eliminate f, and so if we do so, since we 3e plus 3f is equals to 0, and then f is equals to negative e. Substituting this in the first and the last equation here results into 3d minus 3e is equals to 0, and then 3d plus 3e is equals to 6. So this is a simple simultaneous equation. If you add the two equations, we get So we could eliminate d, and by doing so, since 3d minus 3e is equals to 0, d is equals to e, and so substituting that into the second equation there, so we get 3d plus 3d is equals to 6, and so 6d is equals to 6. So we begin by saying that d is equals to 1, and since d is equals to e, then e is equals to 1. As we knew, f is equals to negative e, f is equals to negative 1. As we saw that b is equals to e plus 2f over 3, then b is equals to 1 plus 2 in bracket negative 1 over 3, and so b is equals to negative a third, and a is equals to a plus d over 2, so a is equals to a third minus a third plus 1 over 2, which is a third. And since we saw c is equals to negative a, c is equals to negative a third. So our fraction 3 times u cube over 1 plus u cube squared is the same as a third times 1 plus u minus 1 over 3, 1 plus u squared, negative a third u plus 1 over 1 minus u plus u squared, plus 1 minus u minus 1 over 1 minus u plus u squared, all that squared. We can play around a little bit. For example, we can multiply 3 both the numerator and denominator, so that in the third time here we get u minus 3 over 3 times 1 minus u plus u squared. So the integral from 0 to infinity of 3 u cube over 1 plus u cube squared is the same as the integral split 4 ways as shown here. As you can see, first of all, let's say this first term is integral 1, second term is integral 2, third term that's integral 3, and then integral 4. So, for the first integral here, that's very simple. That's the same as a third of a natural logarithm absolute of 1 plus u plus e. Second integral is also simple because the power u, we just say that would be negative of 1 over 3, 1 plus u plus a constant. The third integral is a little bit complicated because as it appears like it is a natural logarithm integral, but we first of all need to reorganize the numerator such that it's the derivative of the denominator. So we multiply it by half. Let's multiply by 2 both the numerator and denominator, so that in the numerator we have 2u minus 6 over the denominator we have. So the derivative of the denominator is 2u minus 1, so we would have to remove the negative 5 out. So we have 1 over 6, 2u, integral of 2u minus 1 over 1 minus u plus u squared minus a 6 of 5 over 1 minus u plus u squared. So the first term there is simple, so we just have that as a 6 times log 1 minus u plus u squared, natural logarithm obviously. And the second term is what we're going to try and struggle with. So we call that integral 5. And how that is solved, 1 over 6 integral 5 over 1 minus u plus u squared du. We would begin by reorganizing the denominator a little bit into a more of a perfect square, so that we would substitute with tan x. And how we would do that, we would say let u minus a half be equal to square root of 3 over 2 tan theta. and so du is square root of 3 over 2 sec square theta d theta, and such that now if we have to transform the limits, the lower limit 0 as u tends to 0, and then root 3 over 2 tan theta is equals to negative a half, because 0 here becomes, this u becomes 0 here, and so tan theta is equals to negative 1 over root 3, and theta is equals to arctangent of 1 over root 3 negative. So as u tends to infinity, root 3 over 2 tan theta tends to infinity, and tan theta tends to infinity, and therefore theta would ideally tend to pi over 2. Therefore, the integral 1 over 6, 5 over 1u plus u squared is the same as 6 from integral from negative arctangent 1 over root 3 to pi over 2 root 3 over 2 tan theta squared plus the square of root 3 over 2 5, and then would substitute for du, which is root 3 over 2 sec squared theta. Now we've done this because this polynomial here can be expressed as u minus a half squared plus 3 over 4. And so that's why this root 3 over 2 is the same as 3 over 4, but we would like to express it in the squared form so that we could factor it out easily. Then that integral now becomes as follows. We would pull out the root 3 over 2 on the denominator side and also on the numerator side. That becomes, because this square part becomes 3 over 4, so since it's in the denominator, that becomes the reciprocal, so we have the 5 over 6 times 4 over 3 from the denominator here, and then this constant here becomes what we see here, root 3 over 2 times the integral from minus tan arctangent of 1 over root 3 to pi over 2. The denominator here, tan squared plus 1 becomes sec squared, and there's a sec squared here in the numerator. So this would ideally cancel one another, and so we have 10 over 6 times root 3 integral of negative tan arctangent 1 over root 3 to pi over 2 of d theta. So that easily becomes what we see here, and so it becomes 10 over 6 root 3 pi over 2 minus arctangent of 1 over root 3. Now the value of arctangent of 1 root 3 can be found here if we have tangent of angle phi, which is equals to 1 over root 3. Then the hypotenuse becomes 2, so we all know very famously that 1 over 2 being the sine of the angle phi would mean that phi is pi over 6. So this angle here becomes pi over 6. So this becomes 5 root 3 over 9 pi over 2, negative becomes a plus, pi over 6. So 5 root 3 over 9 times 4 pi over 6 is the answer. And if you simplify that further, it becomes 10 times root 3 over 9 times 3 times pi. So this next integral of u minus 1 over 1 minus u plus u squared can be simplified further by, as you can see, we'll multiply 2 both in the numerator and denominator, so we have a half there, and next we have 2u minus 1, 1 minus u plus u squared. This allows us to simplify the integral a little bit further, and then we subtract with the extra one here. So we have a second integral. We've created two integrals from the previous integral. And the first integral there is a easy as saying that's the that's the same as negative 1 over 2, 1 over 1 minus u plus u squared. The second integral is what we're going to try and deal with a little bit in detail. So that we call integral 6. So integral 6, which is half of integral from 0 to infinity of 1 over 1 minus u plus u squared squared du, is the same as we use the same technique where we express things in perfect squares at the denominator here by using 1 minus a half squared and letting that being equal to tan square root of 3 over 2 tan theta, such that du is the same as square root of 3 over 2 sec square theta d theta. And again, transforming the limits would mean that the lower limit theta tends to negative arctangent of 1 over root 3, and in the upper limit, as u tends to infinity, theta tends to pi over 2. So simplifying the integral would mean that now we have root 3 over 2, because now we've pulled the root 3 on the sec square side, and then this half, it becomes now root 3 over 4. Integral from negative arctangent 1 over root 3 to pi over 2 of 1 over root 3 squared over 2 sec squared squared. So we have square squared there. So the first square would cancel out the sec square theta, and so we are left with a 9 over 16 sec squared theta squared, and so one of the sec square theta, as I said, would cancel out, and so we are left with 4 times root 3 over 9 integral 4 minus arctangent 1 over root 3 to pi over 2 of 1 over sec square theta, which is cosine square theta. So using the double angle formula, that's the same as cosine 2 theta plus 1 over 2. So again, we know what arctangent of 1 over root 3, that is the same as pi over 6. So when we integrate this further, we get 2 times root 3 over 9, half of sine 2 theta plus theta, from minus pi over 6 to pi over 2, which is the same as 2 times root 3 over 9, half of sine 2 theta, pi over 2 minus sine 2 minus pi over 6 plus pi over 2 minus pi over 6. So this becomes 2 root 3 over 9, a half of 3 over 2 plus pi over 6, which can be simplified further as 2 times root 3 over 9 square root of 3 over 4 plus 4 pi over 6, which is as simple as a sixth plus 4 times root 3 times 9 over 9 times 3 pi. So getting back to the original integral, which was split into 4 different terms, we saw that the first integral there amounted to a third of natural logarithm of 1 plus u absolute from 0 to infinity. The second term was the same as negative a third 1 over 1 plus u, and so that negative with this minus here becomes a positive, all that from 0 to infinity. The third term was the same as a sixth natural logarithm of 1 minus u plus u squared from 0 to infinity. Notice I've not used absolute terms here because this polynomial is always going to be greater than 0. Then the third integral there meant that we would split it into two, so that the second one was integral of 5 over 1 minus u plus u squared times the sixth. The fourth integral there also got split into a half, negative a half, or times 1 over 1 minus u plus u squared from 0 to infinity, minus the integral of a half of 1 over 1 minus u plus u squared squared. So the integral here was dubbed number 5, and the last one was termed as the sixth integral. So this further would, by combining the first and the third term, would result into a third of log of absolute of 1 plus u over square root of 1 minus u plus u squared. Now this square root sign came from playing around with this sixth term here, where we took up the 1 over 2 constant, and so we're left with just a third. And so now we have this fraction here under the logarithm function from 0 to infinity, and then the rest of the terms just remain as they are. So this is the same as limit as u tends to infinity, and by pulling the u squared, the u term out, under the square root sign it becomes squared, and so we are left with 1 plus 1 over u on the numerator, and the square root of 1 minus 1 over u plus 1 over u squared. So as u tends to infinity of that, minus as u tends to 0 of the same function, and then the second term as well, u tends to infinity of 1 over u minus limit of u tends to 0 of 1 over u. This third term remains as it was previously. The fourth term again minus half of limit of u tends to infinity over 1 over 1 minus u plus u squared minus limit of u tends to 0 of 1 over 1 minus u plus u squared. The last integral there remains as it is. So as we saw previously, as u tends to infinity, this becomes 0, and as u tends to 0, the first term becomes also 0. For the second term, as u tends to infinity, it's 0. As u tends to 0, that becomes 1. The third term, as we saw in the previous integral, that is 10 times root 3 over 9 times 3 pi minus, here as you see, as u tends to infinity, 0, and as u tends to 0, that's the same as 1, so it becomes a half times u minus 1, and the last term we saw was the same as a 6 plus 4 times root 3 over 9 times 3 pi. When we clean up the expressions there, this becomes negative a third. That value remains, and then this becomes positive because we have a negative, so positive a half minus a 6, and this negative interacts with this positive, so it becomes minus 4 times root 3 over 9 times 3 pi. So minus a third plus a half results into positive 1 over 6 plus 10 times root 3 pi over 9 times 3 pi minus a sixth. So this is 2 6 minus a sixth. This would cancel out. Minus 4 pi minus 4 times root 3 over 9 times 3 pi. So this, as I say, this would cancel out. And then the 10 and the 4 here becomes 6 times root 3 over 9 times 3 pi. And so 6 divided by 3 results into 2. So we have the final answer as 2 times root 3 over 9 pi. So this is the final answer. It is a very long problem. I really wonder how the contestants needed to answer that within the 4-minute time limit. I mean, I see portions within the solution that could have been shortened, especially as regards to trying to handle the partial fractions. There's a quicker method to solving that. But I hope you appreciate how these problems can be really intricate and how the solution can be derived. For those of you who have not subscribed to our channel, please do subscribe. We do request you to subscribe. It helps us give us that extra profile that we need just to keep this work going. But I also encourage you to subscribe because you will get a notification each time we upload a video with these very interesting solutions to very complicated solutions, these complicated problems. Thank you. Until next time, it was great interacting with this problem.